Hi, everyone. My name is Colin Raffel, and I'm here to talk about some things that I've done in the past with attention. Yeah, today I'm going to be talking about machine learning models with attention. And attention refers to the ability of a model to refer back to entries in its input when producing each element of an output sequence. So, shown on this slide are sequence-to-sequence models with attention. Sequence models are models that transform one sequence to another using recurrent neural networks. And you can visualize where in the input the model was attending when producing each output element, which is what's shown here in the purple lines. So in the top, we're doing English to French translation. And you can see, for example, that when the model was producing the word économique in the French sentence, it was attending to the word economic in the English sentence. And on the bottom is speech recognition. At the very bottom of the slide, you can see the spectrogram of the speech utterance that's being transcribed. And then at the top are the characters of the speech utterance that the model produced. And the model effectively attends to each region in the input speech utterance that corresponds to each letter that it's transcribing. So that's just kind of a high-level overview of what attention can do. And so here's a schematic of this type of model, this sequence-to-sequence model with attention. And let me give you a little overview of this model so that we're all on the same page. So in the top left, an encoder recurrent neural network ingests an input sequence and produces a sequence of hidden states. And these states are used as a memory, which is attended to while the model is producing the output sequence. So at each output time step, a decoder RNN compares its state to every entry in the memory and then induces a probability distribution over the memory, which is what's shown in these gray boxes in the middle. And then a context vector is constructed as the weighted average of the memory, weighted by the probability distribution. And then, given this context vector, the decoder RNN updates its state, taking as input the context vector, its previous state, and its previous output, and finally produces a new output. So this process is repeated until, for example, an end of sequence token is generated. So from the examples before, the input sequence, like the English sentence, would be passed through this encoder RNN to produce a sequence of hidden states. And then the decoder RNN would produce the French sentence, all the while attending back to the hidden states from the encoder RNN, which correspond to entries in the English sentence. So now I want to take a step back and talk a bit more about specifically what about the attention mechanism is so useful and why it can work so well. So here's another schematic of what an attention mechanism does at each output time step. So the input sequence H, or the hidden state sequence H from the encoder RNN, is shown at the bottom, which has T entries in it. And each entry in the sequence is passed through a small neural network shown in the top left corner. And this neural network produces a single energy or affinity value for each entry in the input sequence. And then these energies are normalized to form a probability distribution that we're calling alpha. So for each entry in the input sequence, there's a unique term alpha. And when you sum up all of the alphas, they sum to 1. So then we compute a weighted average of this input sequence where the weighting is determined by alpha. And this weighted sum is used to compute C, the context vector, which is then used downstream in the model, like for example in the decoder RNN. So to summarize, the attention computes a weight for every entry in an input sequence and then computes a weighted average of the input sequence. And that gives you the context vector. And note that you always get a single vector out of this operation, regardless of how long the input sequence is. So regardless of the value of T. And so let's try to provide some insight into why attention works. And let's consider this toy problem, which is used to test recurrent neural networks. The task is simple. You're given an input sequence with 2 dimensions, one which is just random numbers between -1 and 1, and the other which is 1 in 2 locations. And there are 2 variants of this problem, where the goal is either to predict the sum or the product of the values in the random dimension at the 2 locations where the second dimension is 1. So at the top is an example which shows an input and an output, and the sum and product of the values in the first dimension where the second dimension is 1. And so notice that when solving this problem, the model has to be able to refer back to points in the input sequence, which are potentially very far apart. So the spacing of the two 1 values in the second dimension basically roughly can determine how far the model is able to remember when producing its output. And the problem is designed in this way to test whether recurrent neural networks can store things in their memory for very long time lags. And now we're going to test attention in a sort of unusual way. We're going to take just the attention mechanism on its own, so no recurrent neural networks, and try to solve these two problems. And by using the attention mechanism in this way, we're basically testing whether it's able to effectively use the input sequence as a memory and refer back to arbitrary points in the input when producing its output. So to summarize, we're going to take the input sequence, compute a weighting value for each entry in it, produce a weighted average of the input sequence, and then predict the correct output value based on that. And so sure enough, attention can trivially solve this problem. And what's shown in the tables here is either the number of training examples in 100,000s required to reach perfect accuracy, or the accuracy over 10 million examples. And note that as long as the attention mechanism learns to focus on the two input sequence time steps where the second dimension is marked 1, it should be able to solve this problem, and it does, for sequence lengths up to 10,000, which is as long as I tested. In fact, it can even solve these problems when the input sequence varies from 50 to 10,000 time steps in length. In comparison, recurrent neural networks typically struggle with these problems when the input sequence length is greater than a few hundred time steps. And note also that when you can just compute an unweighted average of the input, it's much harder to solve these problems. So what this simple experiment shows is that one huge benefit of attention is that it allows you to bridge really long time lags in your input sequence, which is difficult for recurrent neural network models to do. So here's an example of extending this idea to a real-world problem. And so here what we're trying to do is actually determine if two audio recordings are recordings of the same song. So for example, you might have one version of a song and you have a big audio recording database, and you want to see if there's another version of the song in the database, but you're okay with the song being played by a different band or played live or on different instruments, etc. So what we're going to do is take a spectrogram of the song, which is just a time frequency feature representation, and feed it into an attention mechanism. And what this will give us is a weighted average of the features in the song, which provides us with a single fixed length vector regardless of the input sequence length or regardless of the length of the song. And then we're going to use the attention mechanism's output as an embedding vector and try to train the network so that audio recordings of the same song have similar embedding vectors, and audio recordings of different songs have different embedding vectors, as measured by the vector's distances. So here's an example. On the left, we have spectrograms for two recordings of the same song, and we pass them both through our model, and we want the embedding shown in the middle to be similar because they're the same song. And on the right, we have two different songs, and we want their embeddings to be different. So as I mentioned, for this network, we're just going to take the input spectrogram, process it with a few convolutional layers, and then feed it through an attention mechanism to get a single vector for the entire sequence. And then we're going to pass that vector through a few dense layers to get our embedding for the song. So just to emphasize, the main power of this network comes from the attention mechanism. Its function is to take the input sequence and distill it into a single fixed length vector, which encodes useful information about the song. To train the network, we have a pretty simple loss function, which I'm visualizing here. Think of the two dark blue dots as embeddings of different recordings of the same song, and the green dots as embeddings of recordings of all of the other different songs. And our goal is simply to push the blue dots closer together and all of the green dots further away from the blue dots. But once the green dots are far enough away, outside of a margin, which is shown here as a yellow circle, we stop pushing them away, and that's it. So if we train a network like this, we get these kind of results. This is a visualization of the embedding distance for same songs, which are shown in blue, like the blue dots, and different songs, shown in green. So you can see the network learns to effectively do exactly what it's supposed to, namely produce embedding vectors who have small distances for songs that are the same and large distances for songs that are different. So we successfully leveraged attention to effectively learn a vector representation of songs, where in the embedded space, different recordings of the same song are close together, and different songs are far apart. Okay, so now that we know that attention works well on its own, let's go back to the setting where attention is most often used in sequence-to-sequence models. And so as a reminder, in this case, the attention mechanism is attending over the hidden states of the encoder RNN. And it produces a context vector at each output time step, which conditions the decoder RNN as it produces the output sequence. If you remember from the first slide, one incredibly useful aspect of attention is that the attention distributions induce a sort of soft input-output alignment, which we can visualize. So each row in this figure shows the characters in speech utterance. So we're attending over the input speech utterance and producing a sequence of characters as output. And each row in this black and white matrix shows the attention distribution for a given output token. And what I'd like to point out is that while this alignment could be arbitrary, it's actually effectively monotonic. And by that, I mean that at a given output time step, the attention probability mass almost never falls before where it was at a previous output time step. And that makes sense for speech, right? Because the region of speech corresponding to the word morning will follow the region of speech corresponding to the word good if someone says good morning. So the correspondence between characters or words in the output and regions of the speech utterance in the input is effectively monotonic. Another thing to note is that attention does allow a soft alignment. This particular alignment is pretty peaky or low entropy. So most of the attention is focused on a particular region in the input speech utterance as each output token is produced. And these things are true to some extent in other domains as well. So here we're translating an English sentence to a French sentence, and you can again see that the attention distributions are somewhat monotonic and pretty low entropy. And there is some local reordering around the middle, but it's worth noting that the encoder RNN could potentially handle this reordering itself, assuming that it's bidirectional. Now, of course, attention does not always have these properties. So here are the attention masks, which are attention probability distributions over an image for an image captioning task. So the goal here is to take an input image and produce a sequence of words that describes the input image. And these distributions are definitely smooth, soft, and spread out, and they're certainly not monotonic for any definition of monotonic. So these observations don't always apply. So here's a schematic view of those input-output alignment matrices we were just looking at. On the x-axis, we have the memory or input sequence, and on the y-axis, we have each time step in the output sequence. So for example, at the first output time step, the model is mostly attending to the fifth entry in memory, which is indicated by the darker gray circle there. And the shading of each dot shows the weight given to the memory entry by the distribution produced by the attention mechanism. And the context vectors we compute are just the weighted average of the memory, which are weighted by these distributions, visualized by these shades of gray. And I'd like to point out that you can view this attention mechanism as optimizing a stochastic process in expectation. So what I mean by that is, let's imagine that at each output time step, a decoder RNN constructed its distribution over the memory as usual, but then instead of computing a weighted average, it uses this distribution as a categorical random variable and samples a memory index and just attends to only that memory entry. So you'd end up with something like the picture here, where each entry in the memory is inspected and a single one is chosen. So the memory entry that was chosen is shown in black, and the memory entries with X's denote that the entry was considered but chosen not to be attended to. And so taking the weighted average of the memory corresponds to computing the expected output of this sampling operation. So in some sense, we can view attention as optimizing this particular stochastic process in expectation. It's also clear that for each output time step, the decoder has to make a pass over the entire input sequence. So it has to inspect every entry in memory at each output time step. And this results in a quadratic time complexity, and also makes it so that you can't use it in online settings where the output sequence is being generated while the input sequence is only partially observed. So we're going to take some of the observations that we made earlier about those attention alignments for different tasks and sort of try to design a different attention mechanism. And so let's just assume that we're working on a task where the input-output alignment is monotonic, sort of like we saw in the speech recognition example and to some extent in the English to French translation example. So let's say that at each output time step, instead of inspecting all entries of the memory independently and choosing one, we start inspecting entries from where we left off at the previous output time step and explicitly process them in a left-to-right manner. And then we assign a Bernoulli probability to each memory entry we inspect and sample a Bernoulli random variable to decide whether to attend to that memory element or move on to the next one. So again, in this schematic, I'm marking memory entries with an X when we decide not to attend to them and coloring them black when we do. So as soon as we decide to attend to something, which is what's shown in black, we stop inspecting memory entries and produce an output token. And then for the next output, we start from where we left off again. And so with this hard attention process, we only make a single pass over the memory when producing the output sequence, and so it's linear time. We can also produce outputs as the inputs come in, so it can be used in online settings. But again, it does induce a strictly monotonic input-output alignment. Okay, so now let's define how we're going to compute the expected output of this hard monotonic attention process. Just like we did when we train a model with softmax instead of using the hard stochastic attention process that I just described. So in order to do so, we're going to replace the probability distribution produced by the softmax in the standard attention with a new probability distribution. And so the equations for standard softmax attention are shown here on the top. So at each output time step I, we first compute an unnormalized scalar energy for each entry j in the memory according to some energy function. This energy function is a function of the state at the previous output time step and the energy and the entry in memory that we are computing energy for. Then we just take these energies and normalize them across the memory with the softmax function, which is what's shown on the second line. So this is standard softmax attention. And so for monotonic attention, we'll compute the attention energy in exactly the same way with the same kind of energy function. Then we'll pass the energies through a logistic sigmoid function, which will give us what I'll call selection probabilities, select ij. These represent the probability that we will select memory item j and output or move on to memory item j plus 1. And so to turn these individual Bernoulli probabilities into a distribution over the memory, we use the equation at the bottom. And this equation is kind of gnarly, so I'll explain it in more detail with a visualization. So here's an animation of the dynamic program used to compute the attention distribution. In this animation, we're computing the probability of attending to the fourth entry in memory at the third output time step. We have to consider the possibilities that at the second output time step, we attended to the first, second, third, or fourth memory entry, which is shown in green and what is being animated. So for the case that we attended to memory entry K at the previous time step, we have to not select any memory entries from K to the fourth entry, shown in yellow. And finally, we have to select memory entry J, shown in blue. So the green sum is over the four possibilities of where we could have attended at output time step 2. The yellow product is reflecting that we have to not select memory entries up to the fourth. And then we need to actually attend to the fourth entry, which is shown in blue. So this gives us a way of computing the attention distribution induced by the hard monotonic process, which will allow us to train it just like normal, just like we do with softmax attention. And so one issue with computing the distribution in that way is that for each memory output time step combination, we have to do this sum and product, which gives training time decoding a cubic complexity if implemented naively. So this is bad because we were originally trying to replace something that was only quadratic complexity. Fortunately, there are lots of shared terms between output time steps, so we can actually write it as a recurrence relation. which is what's shown here on the second line. And this equation also should make some intuitive sense. So from left to right, first we have the probability of selecting memory item J, then we take the attention probability we computed for the previous memory entry and correct it by dividing out the probability of selecting memory item J minus 1 and multiplying by the probability of not selecting memory item J minus 1. Finally, we add the possibility that we attended to memory item J at the previous time step, all the way on the right there. And now this is still bad because it's a recurrence relation, so we have to calculate the terms of the probability distribution sequentially. In other words, we can't parallelize the computation of this attention distribution like we do with softmax. But fortunately, we can solve the recurrence relation and express it in terms of cumulative sums and cumulative products, which are parallelizable. And there's a full derivation of this in the paper at the bottom of the slide if you're interested in how to figure this out. So one last thing I haven't addressed, which is that I described this hard monotonic attention process, which allows for online and linear time decoding. But then the training method I just described isn't hard or linear time, and it wouldn't work for online decoding because we still compute a probability distribution over the entire memory. But the idea is that we're going to train the model in expectation and then use the hard process at test time. So in order to do this, we need to ensure that the selection probabilities are effectively discrete, effectively binary. So the behavior is similar at train and test time. And we're just going to take a simple and common approach here where we add Gaussian noise before the sigmoid activations. And this figure shows the effect of this. Basically, in order to transmit information through the sigmoid, the network needs to make its activation substantially larger than the standard deviation of the Gaussian noise. And if you're familiar, this trick is extremely similar to the Gumbel sigmoid or binary concrete approach. Okay, so now I'll present some experimental results. We ran experiments on online speech recognition on the Timmett and Wall Street Journal datasets, sentence summarization on the GigaWord dataset, and machine translation on the IWSLT English to Vietnamese translation task. And so here I'm showing the word error rate for the Wall Street Journal dataset. And lower is better because this is an error rate. So this slide is going to be the only raw numbers slide that I'll show for this particular paper, since the relative performance of different models was similar for all of the experiments. And so all of these speech models have unidirectional encoders. The soft monotonic and softmax models were offline because of their attention mechanisms, but the models shown in blue with blue bars could be used online. As is generally the trend, a standard softmax attention slightly edged out soft monotonic attention, which was slightly better than hard monotonic attention. So what this basically means is that you only sacrifice a little bit of performance to get a online and linear time model, which is the hard monotonic model. I also tested the model with a CTC loss, which did it quite a bit worse. CTC is just another way of training sequence-to-sequence models. And the policy gradients result is using a similar model, but instead of training in expectation with the probability distribution that I just described, they keep the attention discrete and use reinforcement learning to estimate the gradients. The weighing et al. CTC model is a more realistic representation of the performance of CTC for this task. So as I mentioned in general, this was the trend of the results. Softmax does the best by a small margin, followed by soft monotonic, and followed by hard monotonic. So a little more informative is to look at the alignments that the model learned. So here I'm plotting the alignments on top and the speech utterance feature sequences on the bottom. And both alignments are for the same feature sequence. Hard monotonic is on the left and softmax is on the right. In speech recognition, the alignments generally end up looking the same between the two attention mechanisms. But there are some minor differences, like the softmax attention spreads out probability and has some minor reordering in places, which I'm highlighting in these red circles. And I'm not sure if this hurts or helps the model, but we'll come back to this difference a little later in my talk. For sentence summarization, we actually use a bidirectional encoder because as far as I know, people don't mind doing offline sentence summarization. So the encoder can actually do some reordering of the input sequence. And we actually see that here. So for hard monotonic attention, the first few words are aligned as we expect them to do. So Greek is aligned to Greek, and government is aligned to finance, approves to approved, and more to more. But the last few words aren't. And the model is able to produce a summary which was not monotonically aligned because the encoder is bidirectional and so can do a little bit of reordering. And you can see that even with the softmax attention, the alignment there isn't obviously what we would expect it to be. And it actually spreads out attention probability a lot, which again, I'm not sure is helpful or not, but we'll come back to later. And so here are some example alignments for English to Vietnamese translation. And here we're using a unidirectional encoder again. And you can see that in order to deal with the non-monotonic alignments, the monotonic attention basically just waits until it's seen enough of the input sequence. Yeah, so if you look at the right, it needs to reorder the words a huge famine, the first three words, which is evidenced by the softmax model on the right, giving an alignment that's non-monotonic. It kind of goes backwards from what we have been expecting. And what the monotonic attention model does is it just waits to attend until the word hit. And then the encoder has seen all of the words a huge famine hit and has probably or hopefully effectively summarized those words in its state at the word hit. So this allows the decoder to have access to the entire region of the input sequence, which requires reordering, by simply waiting and attending to the encoder state at the end of it. And so you can see that a fallback mode of this model would effectively be to attend completely at the end of the input sequence. And that would effectively make the model fall back on a sort of standard sequence-to-sequence model with no attention, if you're familiar with that. So as I've mentioned, one motivation for this approach is that it is potentially much more efficient because the hard monotonic decoder can run in linear time. And so to test how much faster it can be in practice, we implemented a softmax attention decoder and a hard monotonic decoder in C++. We only implemented the attention mechanism functions in order to isolate the differences in speed. So no recurrent neural networks here, just the actual attention mechanism. This plot shows the speed up for different sequence lengths. So we get a speed up between 4 and 40x, depending on the input and output sequence length. And you should also recognize that if you have a model with a very large RNN encoder and a very large RNN decoder, those things are going to take up a lot of the computation in your model. And so you can think of these speedups as sort of an upper bound on what you might expect to get in practice, depending on the size of your model and your input and output sequence lengths. So I showed how this monotonic attention can give us online and linear time decoding, but we also found that on all of the tasks we tried, it hurt performance a bit compared to softmax attention. So one reason for that might be that the model is forced to attend to a single entry in the memory at each output time step. So unlike softmax attention, the attentions were not soft, as I pointed out a few times. So here I'm showing a schematic of a potential fix. And this is very recent work, actually the first time I'm talking about it publicly at all. So the idea is simple. You do monotonic attention as usual, but then instead of only attending to a single item in memory, you attend over a fixed size chunk of memory before where you decided to attend to. So the attention over each chunk is just done with a softmax. And here I'm showing a chunk size of 3. So the memory entries shown in bold circles are the ones the monotonic attention mechanism decided to attend to. So this gives you the ability to do a soft attention, but it's still online in linear time. And we call this attention mechanism MoCA, for monotonic chunkwise attention. And now to train it, we only have to tweak the monotonic attention equations a little bit in order to get the expected output of the attention mechanism. And so at the top is the monotonic attention equations from before, just as they were. But after we compute the monotonic attention distribution on that second line, we're also going to compute a new set of energies for the softmax attention. Then to compute the attention distribution for MoCA, we simply compute softmax distributions over all possible chunks of the input sequence and weight each chunk by the monotonic attention probability, the probability of stopping at that point, which is what we're showing on the bottom. And fortunately, we can still write this whole set of equations in terms of cumulative sum and cumulative product operations. So just like the other monotonic attention mechanism that I described, it's very efficient to train. Okay, so that was a pretty simple tweak. One issue with that approach is that we have to choose a particular chunk size, which gives us a hyperparameter that we might have to tune. Another option is to let the chunk size be set adaptively. So imagine that the chunks are set to be the region of memory between where we attended at the previous output time step and the current output time step. So for example, at the second output time step, the chunk spans from the second entry in memory, which is where we attended at the first output time step, to the fourth. And again, I'm showing the location where the monotonic attention attends to at each output time step as bolded circles. And the shading of each circle denotes the softmax attention and probability for each chunk. And we're going to call this monotonic adaptive chunkwise attention, or MACHA. And the math for computing the attention distribution for MACHA gets a bit hairy, so I'm not going to present it here. But suffice it to say, you can still train it in expectation, and you can still train it completely in parallel with cumulative sum and cumulative product operations. But this gives you sort of an adaptive way to attend over chunks in the input sequence with a soft attention. Okay, so how does this help us? Turns out it does quite a bit. So here we're showing results on Wall Street Journal again, and you can see that MACHA and MoCA both close much of the gap between monotonic attention and softmax attention. And there seems to be a trend that softmax attention does maybe a little bit better, but it's hard to measure due to the variability in these results. So the error bars show the standard deviation for 4 trials, and none of MACHA, MoCA, or softmax are significantly better than the other in these trials that we ran. And just as a reminder, we can still get the benefit of online and linear time decoding at test time with either MACHA or MoCA. So these are online and linear time models, but they perform almost as well or as well as softmax attention, at least on the Wall Street Journal task. We're still doing experiments with these models, and so we'll have some more concrete results hopefully soon. So here's a picture of real-world alignments produced from these experiments. So on the left is MoCA with a chunk size of 2, which we found worked quite well. You can see that it basically attends over a small window of 2 frames at each output time step. But it's a fixed, specific 2-frame chunk all the time. And then on the right is MACHA. You can see exactly the same behavior as we designed. So it does soft attention over the region between where it attends at each, where the monotonic attention attends at each time step. And note that these alignments aren't for the same speech sequence, so sorry about that. But this will give you an idea of sort of the behavior of these 2 new attention mechanisms. Okay, so that's all I'm going to be talking about today. I'd like to thank my collaborators who are shown on the top here. Dan Ellis, who was my PhD advisor, CC, Tong, Peter, Ron, and Doug, who I now work with at Google Brain. And on the bottom there, you can find references to the 3 papers that I focused on today, if you want to read more. And thanks for your attention. I'll see if I have any questions. Thanks. Cool. So Katerina has a question. How can we measure the level of attention at a certain time step? So the level of attention basically is what comes out of the attention probabilities as you compute the output. So for example, in softmax attention, when you produce a certain output token, you're going to put the distribution over the input sequence. And each term in that probability distribution is the level of attention for each time step in the input sequence. So Mel FK asked, can we also apply this for pitch recognition? Let me think about this for a second. Yeah, so fundamentally what a lot of these models are used for is sequence-to-sequence problems. So what you'd have to do is be able to represent your output pitch that you want as a sequence. So let's say you had your input audio and you computed a spectrogram just like I showed early, then you'd have your input sequence. For the output, if you were willing to produce like a sequence of pitch values and maybe times, or even just like a sequence of notes and their onsets and offsets, then this framework could potentially definitely work for that. So Yang Liu asks, "Do you have a GitHub link to how to implement attention?" Yeah, I should have put a link in the slide, but all of the attention mechanisms that I described today, so that includes softmax attention, the and the monotonic attention, but not mocha and matcha yet. But monotonic and softmax and some other attention mechanisms are all implemented in TensorFlow. So if you have TensorFlow installed, it's in the tf.contrib.seek2seek module. That's numeral 2. And so if you want to try things out with attention, that's a great place to start. There are also some tutorials, the code of which I used for some of these experiments, available from TensorFlow for doing sequence-to-sequence transduction, in particular for machine translation and text summarization. So what are your, Toronto AI asks, what are your thoughts on using standard normalization for an attention chunk instead of softmax? So I'm guessing by standard normalization, you're just thinking, okay, I have a sequence of numbers. I'm just going to normalize them to be between 0 and 1. I think that could definitely work. The only thing I think you'd have to do is transform them so that they're all positive first. Softmax has some nice properties. One is that it's sort of offset invariant. And by that, I mean that if you shift all of your softmax energies by a constant, the distribution on the output doesn't change. And it also is like somewhat scale invariant. It's not fully scale invariant, but if you change the scale of your energies a little bit, then the distribution won't change a lot. And so these things, I think, make it a little easier to optimize. And Katerina asks, have you tried the same approach for video processing? So I haven't worked with video at all. Video is tough because the input sequences are so long and the shape of the input, the images, are so big. So you could imagine wanting to do something like maybe in the simplest case, like lip reading, where you have a video of someone talking and you want to produce the sequence of words that they said. And people have used sequence-to-sequence models for that. For more complicated tasks, I'm not aware of any work along those lines. But I would imagine that monotonic attention would work pretty well for example, lip reading. So Jin Hasim said, I believe Jimmy Ba worked on stochastic-based attention, and asks, what are the benefits of a stochastic-based model versus a deterministic model? Yeah, you're exactly right. Jimmy did some early excellent work on hard stochastic attention trained with reinforcement learning. And so in terms of the benefits are similar to what I described here, namely that they are potentially, they don't have the same quadratic complexity that softmax attention has, because you don't have to attend to the whole input. You can just attend to a particular point. The benefits of the soft attention model are frankly that it's very easy to train. Soft attention often, especially softmax attention, often just sort of works off the shelf. When you use stochastic attention or a hard attention, as Jimmy did, where you're using reinforcement learning to train it, you have to do gradient estimation, and gradient estimation is hard to get right, especially in sequential models. I do have some other work that I didn't talk about today because it was mostly done by other people, but I just helped out a little bit, on training a hard attention sequence-to-sequence model with reinforcement learning, specifically with Vimco. And you can find that on my website. And that's some cool work to check out if you're interested in that line of research. So Vox Mente, I think, asks, have you released code for Matcha and Mocha? Not yet, but I will. It probably will end up in TF Contrib Seek2Seek, and hopefully in the not too distant future. So those experiments and that research is pretty new. So Overcode says, I didn't understand a lot of things from this talk. However, it caught my interest. What can this be used for? Any applications in mind? So sorry if you didn't understand a lot, but hopefully, yeah, I'm glad it piqued your interest. In terms of what it can be used for, most of what I talked about today were sequence-to-sequence models. So anytime that you have an input sequence and an output sequence, like English sentence, French sentence, speech utterance recording, words being spoken, sequence-to-sequence models have proven very effective in these settings. For the earlier stuff I talked about, where you're just distilling a sequence into a single fixed-length vector, anytime that you want to do similarity between sequences, that's a powerful way to do that. So those are some examples. Blurb says, can you use it for large images, slicing each image vertically and then attending to each slice? So you can definitely use attention for images. And earlier in the talk, I showed Kelvin Chu and Jimmy Ba and their co-authors work on doing visual attention for image captioning. And they didn't slice it up vertically and attending each slice. They actually just attended to the 2D grid of the image. I think either would probably work okay. The reason that it's nice to do things that way is that you can just use a ConvNet on the input. You don't need an RNN on the input. And yeah, and I see your note now, but you can't if the image is too big. So about to get to that. If the image is very big, then softmax attention can get extremely expensive. That's one of the reasons that Jimmy proposed his hard attention, which should help with that a little bit. The other thing to look up if you want to do attention over very big things, such as images or even just really long sequences. There have been a couple papers along these lines. There was one paper from Brain called Learning to Remember Rare Events, which does sort of an approximate nearest neighbor lookup instead of computing attention over all of the input sequences. And there's another work from DeepMind called, I'm not going to remember that paper's name, but it's basically doing a sparse lookup for attention. I also would imagine that could work on things like very large images. So Overcode asks, when the word attention is used, is it related to human attention in some way? And so that's the hope. I mean, there's no direct link, but the idea is that you allow the model to attend or pay attention to things just like we do. So, when you listen to someone speaking and you're hearing a particular word, you might think you're paying attention to that particular word that they're saying. It's maybe more explicitly true doing the image captioning stuff where the attention happens over a particular region in the input image. And but this is a very loose correspondence. But that's sort of the idea, yeah. So Mel FK says, for pitch recognition, like determining notes or timing of something being played, how much sample data would you think is needed, and which algorithm, Matcha and Mocha, would give a better result based on my experience? So yeah, all of these models work better with lots of data because they tend to be big models and very powerful models that have an easy time overfitting. So the more data you can find, the better. I realize that's not a very helpful answer. It doesn't give you a concrete number, but I would say get as much data as you can get your hands on. Try to train a standard model to do what you want it to do, and if you get a lot of overfitting, then collect more data, especially if you've already added regularization. And which algorithm? So what I would actually recommend people do is start with softmax attention. Softmax attention is a little easier to get working than the monotonic attention and the variants Matcha and Mocha that I talked about today. Because of softmax being a little easier to optimize than the sigmoids is really what it comes down to. It's easy to saturate the sigmoids and have the attention mechanism sort of fail to learn. They are pretty robust, and often you can just drop them in for softmax attention, but I would start with softmax attention, and then given that you want online and linear time decoding, which would make sense for pitch recognition if you wanted to recognize pitches as someone is playing something, then investigate monotonic attention, Matcha, and Mocha. I mean, I'm saying this tentatively at this point, but I think it seems like Matcha and Mocha both will work a good bit better than standard monotonic attention. So I would suggest trying either of them. It's not obvious which one is better yet, but those are, as I said, ongoing experiments. Thank you all again for your questions. Hope you enjoyed the talk.